Hi, in this video we are going to implement a linear regression application together, so let's get started. The aim of the application will be the following. We have some training data we can download, for example, from the web, that we would like to make prediction that if we have a certain size of house, what's the price of that house. And of course there's lots of data on the web, for example, that you can download the size of the houses and you can download the according prices of those houses, and we can make a simple linear regression. This is the simplest model, of course, and sometimes it is very powerful, and typically in this case, as far as house prices are concerned, it is very straightforward. But for example, if we would like to predict stock market prices, we would have to use much more complex techniques such as logistic regression. We are going to talk about it later. But here we are going to make a simple linear regression. So I'm going to import from SciPy, I'm going to import the stats. I'm going to import the NumPy. With the help of NumPy, we can manage array-based techniques very easily as MP. Then I'm going to, in order to be able to plot these kinds of stuff, so I'm going to import the matplotlib import pyplot as plt. Then I'm going to have the training data x. It is going to represent the size of the houses, and for example that array, I'm going to have the size 112, for example, square meter, whatever. It doesn't matter, it's just for demonstration purposes, of course. 345 square meter, then this 305, 372 square meter, then the very big houses 420, and then 578. So this X is going to represent the training data, and this is just the size of the houses. The Y, the training data, is going to represent the prices of this house. So of course it is going to be that the size of these arrays are the same, because this is the first house, and the first item in this Y array is going to be price of this house. Then this house, I mean the house with this size, because these are the sizes, and there I'm going to print the prices accordingly. For example, approximately $1,000. Not so realistic, whatever. Yes. Then 2,200, 2,600, approximately 3,200. Okay, and approximately 4,460. Okay, so this is the size of the houses, and this array represents the prices of these sized houses. So of course accordingly. So this is the size and this is the price. First of all, I would like to fit a linear model, the linear regression line, to this kind of data set, and I would like to get the slope, the intercept, and some statistical data such as the R value, the P value. I'm not going to use these, but anyways, the standard error, sometimes it is very important. It is going to be equal to the stats that lin regress, and of course I have to specify the X and the Y training data, because these are the training data, and after the training we would like to make predictions. So for example, I'm going to plot plt.plot this X, this Y. I would like to plot it with round objects, and the color of these circles will be black, for example. And of course, I would like to make some labels. The y label is going to be the price, and the plt.x label is going to be the size of house. Okay. And for example, the axis, I want to be the axis, the x is from 0 to 600. There's no need to be greater because the greatest item is approximately 570. And the y range will be from 0 to, for example, 5000. This is the greatest number, so there's no point in setting it to, for example, a million or whatsoever. Then, first of all, I would like to run this and show the plot. So if I run this, I have to call the plt.plot. Sorry, plt.plot. Okay. So if I run it, I'm going to get not that plt.plot, but the plt.show. Okay. So these are our points. We have the size of houses on the x-axis, we have the prices of these houses on the y-axis, and we have the given points here. And these points are these points. This is the x, this is the y, this is the x, this is the y, and so on. So this is our data set. We would like to fit a linear model, a linear line, and this is what linear regression does. So I'm going to plt.plot, and I have already calculated the slope and the intercept with this stats.linregress method. So I just have to ask that the slope plus the intercept, it is going to give us the line we are looking for, and I would like to use the color blue, and that's why I use this B color. Okay, so this is the line. I'm going to rerun our algorithm, and yeah, there's a beautifully fitted line, and this stats.linregress calculated all the parameters we need, the slope and the intercept. And here's the interesting part, because with the help of this model we get this line. So whenever, for example, we have prediction, we want to make prediction. That's why we use this model, because for example we have the new data and we would like to calculate the price of a house that have the size, for example, 150 square meter. So I just have to print that, for example, I'm calculate result is equal to the data times the slope plus the intercept. I'm not sure whether you are familiar with this algebra, but equation of a line is something like this: a times x plus b, when the a is the slope and the b is the intercept. And that's what this linear regress calculates for us, the slope and the intercept. So whenever we want to get the y, we just have to use this formula, and that's why I use this. Okay, so we get the result, which is the y. I mean that this result is the price of the given house. So maybe it would be that new x and new y. So print, for example, the new y. I can make a prediction that it is going to give us the predicted price for a given size. This is the size in square meters, for example, and we would like to get the price. So I think that 150 something here, it should be approximately $1,500. Let's see whether it's true. Data.slope.intercept, data is not defined. Oh, okay, because I renamed it to new x. True. I'm going to rerun our algorithm. So again, approximately something like this, and yeah, it worked fine. The predicted price is exactly $1,549. So this is why, and I don't want to repeat myself several times, but this is why it's important, because we have some training data. Then we have the linear regression, and we have a linear model. We fit a linear line. And then after the fitting, we are able to make predictions. I have a new data, 150 square meters, and I would like to know the price of this house. And I can calculate it because I have already calculated the slope and the intercept because of this diet.linear regress. So that's all about linear regression. Thanks for watching.
Hi, in this video we are going to talk about logistic regression. So let's get started. Imagine a situation where we're working for an insurance company and we want to make prediction according to the balance on credit cards, and we want to predict whether the given person can pay back the debt, the loan. And of course there are two categories: no, which denotes zero, and yes, which means that he or she can pay back the debt. And unless in linear regression we have only two categories, and we come to the conclusion that if the given person has very little money on the credit card, he or she is not going to pay back the debt. So it's unlikely that this person is going to pay back the loan. And that's why there's a zero in the three axes is near zero or no. And if there's lots of money on the credit card, there's a high chance that the given person is going to pay back the debt. So that's why there's a 1 or a yes. And if we use linear regression for this model, it is not a good approach. And why? Because if we have an outlier, as you can see, the rightmost x, then it is very sensitive to these outliers. Now the linear regression model is going to give us a very bad prediction, because if we use this line, this linear regression line, to predict the outcomes, as you can see that even if the given person has a high balance, so for example $800 on the credit card, we predict that he or she is not going to able to pay back the debt. When the given situation, according to the data, we can come to the conclusion that if she or he has $8,000, he can pay back the debt. And we call this situation, I'm not sure whether you are familiar with financial engineering stuff or whatever, but it's the probability of default. So we say that the person is going to default, which means that he or she is not going to pay back the loan. So that's why this linear model is not good. And another aspect is that we want to predict probabilities. That, for example, there's a 90% chance that a given person is going to be able to pay back the loan. So, for example, this sigmoid function, or this function we have been plotting here, is a better predictor, because it is between 0 and 1, and we want to assign a probability to each balance. And the linear regression model, it is out of the range, so it can be bigger than 1 and it can be smaller than 0. So that's why a linear model and a linear regression is not good in these kinds of situations. And this is the same situation when, for example, we want to classify emails, whether it is a spam or it is a normal email, or we want to predict whether a given tumor is going to cause cancer or not. So in these kinds of situations, logistic regression can be very useful. And we have the x-axis, which is the balance on the credit card, as we have discussed. We have the y, which is paying back the debt. And we have two categories, the yes and the no, the default and the not default. So this is the logistic function, or the sigmoid, and if you are familiar with higher mathematics, this is the function for the sigmoid function. I denoted with gz, which is equal to 1 divided by 1 plus e to the minus z. This is the sigmoid function. And For example, if we use a linear model for logistic regression, we come to the conclusion that this gz is equal to the same as we have discussed in the first equation, but the z is equal to a beta 0 plus beta 1 times x, where the x is the balance on the credit card. And this is the so-called Ajax heuristic, and with the help of this heuristic we will be able to predict whether a given person is going to default or not. So for example, there's an X, for example $500. What's the probability for a person that has $500 on his credit card that he's going to default? And we can calculate this probability with the help of this sigmoid function, with the help of logistic regression. And this sigmoid function, as we said earlier, it has a property that it's going to be greater than 0 and it's going to be less than 1. So if it's minus infinity, the z is equal to minus infinity, then this g sigmoid function is going to be 0. If the if the z is equal to 0, the value of this function is going to be 0.5, and when the z is equal to plus infinity, the sigmoid function is going to be 1. So it's very good because it's always in the interval of 0 to 1, so it is good for predicting probabilities. And if you are familiar with probability theory, the probability must be between 0 and 1. So that's why the sigmoid function is very good. Okay, so logistic regression is a linear classifier. We have to fit the beta parameters first. What are the beta parameters? As you can see in the second equation, they're the ae to the minus b0 plus b1 times x. And we have to find this b0 and b1 parameter to be able to make good predictions. So we have to fit the beta parameters first, and after that, the gz is going to give us the predictions we are after. So the Ajax is the so-called hypothesis. The Ajax, as you can see here, is this gz function, but the z is equal to b0 plus b1 times x. So we have a linear model. And this Ajax is the so-called hypothesis. It is going to tell us the probability of y equals to 1. What does it mean, y equals to 1? That this person is going to pay back the debt. This y can be 0 or 1. The 1 is the fact that we have been discussing, so the person is going to be able to pay back the loan, and the 0 is the probability that he or she couldn't pay back the loan. And of course we have to have a given x input. So we come to the conclusion that the Ajax is greater than equals to 0.5. That means that y is equal to 1. So this is a no default situation, which means that the person can pay back the loan. If the Ajax is smaller than 0.5, it means that the person will default. And it is the same as the z is less than 0, which means that he's going to default. If the z is greater than 0, it means that he or she can repay the debt. And if the z is equal to 0, that's what we call the decision boundary. So for example, let's consider a classifying situation like this. We have the x1 and the x2 axes, and we have the red dots and the yellow dots. And we want to find a decision boundary, as we have discussed here. So if the z is equal to 0, this is the decision boundary. And what is the z? The z is equal to b0 plus b1 dot x, which is a linear model. So for example, here we see that we can separate these two clusters with the help of a single linear line. So this can be the decision boundary. And how can we find it? We can make a prediction that y equals to 1 if we are over the decision boundary, and below the decision boundary the y is equal to 0. So for example, the Ajax, which is the hypothesis, if you remember, can be the g function of b0 plus b1 times x1 plus b2 times x2. This is our model. we have the freedom to choose these parameters, these x1 and x2 parameters, and we see that this model can separate it. I mean, these clusters can be separated with the help of a single line, and that's why our model is linear. So we have the x1 and the x2 without any square root functions or polynomials and so on. And what is the g function? The g function is the sigmoid function. So you just have to put these numbers, I mean this linear model, to this function, this gz, 1 divided by 1 plus e to the minus z, and here in our model the z is equal to this b0 plus b1 times x1 plus b2 times x2. Okay, so we can calculate the beta values with the help of gradient descent. So we have a cost function and we have to minimize it, and we come to the conclusion that the beta 0 is equal to -3, the beta 1 and the beta 2 is equal to 1. So this is the important step to find these parameters, and we can do it with the help of gradient descent. If you are interested in the deeper mathematical background, it's going to take about approximately 200 hours to get a good grasp of the mathematical background of machine learning. But there are lots of important and helpful videos on YouTube, for example. So this is the decision boundary, and by the way, you can use these kinds of techniques, the linear regression, support vector machine, without the concrete understanding of these mathematical formulations. As far as I am concerned, I'm interested in it. So we have to find a decision boundary, and now that we have found the beta parameters, we can write the equation of the decision boundary, which is x2 is equal to 3 minus x1, which is the equation of this line we have drawn here. So the intersection with the x2 is +3 and the slope is -1. So that's all. If you are familiar with higher math, this is the equation for this decision boundary. But we can use this logistic regression for complex systems. For example, situation like this. We want to create a model that will be able to detect whether this cluster is going to be a red or it's going to be a yellow. So in our model, as we have discussed earlier, we are the ones who create these models. And in the previous example, we used the linear model. Here, our model is going to be that the b0 plus b1 times x1 squared plus b2 times x2 squared. We know that we have to use some equations of a circle, and if you are familiar with higher math, this is exactly the equations of a circle. So it's going to define a decision boundary like a circle, like this, and we can apply our logistic regression to solve this problem. So basically, this logistic regression is a classifier problem, and it's very, very helpful and very, very efficient. And why is it good? Because we can predict the probabilities. Linear regression is helpful because we can have a guess. For example, we have certain size of house and we can predict its price. But we are not able to predict it, for example, say that we can say it with 90% a probability that the price of this house is going to be that and that. We can't say that, but with the help of logistic regression, we are able to assign probabilities to each guess, and it can be very, very useful. So that's all about logistic regression introduction. Thanks for watching.